I am the head of data and AI at Bowery Farming, and this not humble title, AI Farming, 100 times the yield with a data team of 1. I have to just say right at the top, there are more people involved, and I'll mention them at the end. So we say Bowery Farming, Bowery the modern farming company. Modern farming is not a self-evident term, right? There are people farming all over the place. They've been doing it for a while. They're doing it now. So when we say modern farming, we mean a specific set of technologies that we're using to make farming more productive and meet all of our needs as a growing world that needs to be fed. So the specific set of technologies that we're talking about are that we are growing indoors. We are growing entirely hydroponically, so there's no soil involved. All of the light in our farms comes from LEDs. So this is not a greenhouse with natural light. It's all being provided by us to the plants. And it's vertical. So we have crops planted in tiers all the way up to the ceiling. And you may have seen this, I'll show some pictures coming up. But that's how you get sort of the highest density of productivity into a room, into a space. And then the fourth piece is that it's automated, right? We want to take more and more of the process of doing agriculture and make it scalable, right? Apply technology to get more of that work done with less and less input. And why? So I mean, that's sort of a cool set of technologies to throw around, but we don't do it just because we are technophiles. We do it because it provides us these things that we all care about. So the first is our farming technology is on the order of 100 times more productive per acre of land. Right? So in a world where we have less and less arable land or less and less space in general, we get 100 times more productivity for a few reasons. If you think about an acre in the outskirts of New York City, our farms are in Kearny, New Jersey right now. How much of the year do you expect that farm is productive growing the produce that you'd like to eat tonight for dinner? Only a little bit, right? Because there's this whole section of the year where it's sleeting and the salt trucks are driving around, right? And that's not great for agriculture. So we get that part. We get to grow year-round. We also get to go vertical, right? So we get that multiplier where instead of using this acre once, we get to use it 7 or 10 times. And then the third piece is, I don't know how many in this urban crowd, how many of you have lawns you have to mow. But you know that day in the summer where it rains all weekend and then it's super sunny on Monday, and by the time you get home from work on Wednesday, the grass is up to your knees, right? It's because there's a set of inputs that plants really thrive in, and outdoors you don't get that all the time, right? You get this irregular input of those input factors. And so in our farm, it's that perfect summer sunny day every day of the year, right? All the light, all the water you could need all the time. And so those together, we can produce produce for all of us to eat 100 times more productively than the same acre of land traditionally. At the same time, we can be resource efficient. And so because we're indoors, because we control our environment really tightly, we don't need any pesticides. So no kinds of regulation of pests or any sort of biological threats to the plants, right? So we don't even have to get into which chemicals are safe to use or any of those things. We just don't use any of it. One of my favorite ones, 95% less water. So because this is a closed system, all the water we give to the plants either ends up in their plant cells as lettuce on your table, or gets transpired into the air and collected and put back into the system. And so we're not dumping tons of water that runs off into the nearby stream. And then finally, we can build these farms close to where people are eating the food. And so what that does is reduce the supply chain complexity and all the supply chain energy, and also delivers a product that is local and fresh for the people that are eating it. So we serve a number of outlets that you're familiar with here in the city. All of that food is created less than 10 miles from where you consume it, right? And so that has a whole bunch of sort of energy and complexity and systemic benefits. So Bowery is a company. We are 3 years old, just turned 3 years old a week or two ago. We have 60 employees currently. That includes everyone who works at the farm and everyone that works in the office in Flatiron. And we have been shipping product to these outlets: Foragers, grocery stores, Whole Foods, Sweet Green recently, and a couple of really nice restaurants in the city for maybe almost 2 years now. So we've been in the market for a long time, and this business is all about not proving that we can bring lettuce to the market, but that we can do it at scale and we can do it better than it's been done before. So, haven't really said anything about the AI yet, right? It's fun to throw around AI, but you have to make sure you're specific what you mean about that and why that's valuable. So I think about AI in our world in 3 pieces. The first is operational. So we have a lot of constrained operation sort of challenges where we need to get the most utilization, the most efficiency out of our farm, because this whole business is based on being able to produce the most product the most efficiently. And so I'll get into sort of an example of each of these later. But there are a lot of things you can imagine. Finding the right home, so crop positioning, finding the right place to put each crop within the farm is a data science problem. There's an AI problem. You can think about task ordering. How do we organize the work so that all the harvest and all the transplanting and all the seeding happens in the most efficient way, in a way that gets the most productivity out of our farm workers? Second category is informational. There's a whole bunch of when you think about someone who has a real green thumb, right, or someone who has a ton of experience in agriculture, has been running a farm for a long time, they're walking around constantly looking at the crops, noticing what's going well, what's going poorly, and making adjustments, right? That doesn't scale very well to our 50 feet tall, warehouse long, thousands of different crops to keep track of kind of a system. And so the opportunity here is how can we extract and structure that data in a way that lets a smaller number of those people use that same expertise to manage a larger number of crops. And so in this world, we have things like computer vision. So how can we have thousands of eyes on these crops that are growing instead of one person walking around, and bring to their attention the things that they need to react to or that they need to interpret or bring their expertise to? And so the AI is sort of in that component is how can we allocate our human attention, right, our human resources to the crops that will most benefit from it? And then third is agricultural, right? Obviously, at the end of the day, what we want to be really good at is growing these crops better than other people have been able to grow them. And so that really comes down to finding the perfect recipe. So in this new indoor farming world, we get to choose a lot of the features, right? We get to choose a lot of the experiences the crop has. How much light, what temperature, how much humidity, how much nitrogen should be in the water, all of these factors that the plants care a lot about, but they care differently. The different crops want different things. And so I think about this problem fundamentally as a high-dimensional search, right? We've got a ton of different levels we could choose in terms of light intensity. We can cross that with how much nitrogen at a bunch of different levels, right? That gives us tons of, potentially millions of different recipes we could try for each crop, and we have to find a way to search that space and find better and better recipes all the time. Now you may be thinking, this is all very techy and exciting and saying AI is fun, but people looking for better ways to grow crops is not new, right? You didn't come up with that. And in fact, that is sort of the definition of agriculture, right? People found things that they wanted to eat, and then they said, I wonder if I could do this a little bit differently and get a little bit more to eat. And we are not doing anything different. So this is an Inca terrace from the 15th century. So not only were they already experimenting 600 years ago, trying to say, if we did this a little bit differently, would we have more to eat? They had already gone vertical. Right? They've already got 9 levels of farming going on there, which is 2 more than we've got. So what's exciting about this is not that we've come up with the idea of doing experimentation, doing data-driven incremental improvement in agriculture. It's that we have this orders of magnitude bigger opportunity in searching that space. So if you think about open field farming, and you think about agricultural opportunities in 2 dimensions. The first dimension on the x-axis here is how much of what the plant cares about do you get to control? So with open field farming, you get to control what fertilizer you put down. Maybe once or twice a year you can control that. You can control how often you rotate the fields, and so sort of roughly what else is in the soil. But you don't get to control the temperature or how much it rains, or whether there's a big storm that damages all your crops, or how much light it gets, right? If it's cloudy all spring. All these huge factors that the plants care a lot about, you just have to sort of take your chances with. At the same time, the other thing that we know, any sort of machine learning problem, any sort of learning problem in general, the most important thing is how many times do I get to ask the question, get some feedback, and iterate. And in the world of open field farming, you plant your crops once per year, right? And you maybe have multiple fields, so you can sort of try a couple of different things per year. But you plant once, you work all season to develop those crops, and at the end of the year, you figure out if you did a little bit better than last year or not. Definitely possible to make progress, and people have been working on that for millennia, but slow going. Greenhouses, right? For the last couple hundred years roughly, give us the opportunity to control more, right? You can control temperature through a much larger portion of the year, and you get more tries per year, right? So you can learn faster in a greenhouse than you can in an open field. Where we are in the world of vertical farming is all the way at this other end of the scale, where we can control almost everything that the plants care about. We get to choose values for all those things. And at the same time, we get to search really quickly through all of those possibilities, right? And so in a farm like this, you can get sort of a first glimpse into the sort of scale we're talking about. Each of those different growing areas there, we can choose all of those different combinations. And so through the course of the year, we get thousands of chances to evaluate a recipe for each crop. And so that equation, right, that control by iteration speed gives us the ability, gives us sort of the opportunity to really drive advances in agriculture. But it sort of falls to the AI team then to deliver on that promise, right? And so one thing that I was most excited about in joining Bowery about a year ago is that these little cartoons were part of the Bowery pitch well before I started, right? This pitch that we were going to close this loop between learning about the crops and feeding back in and growing more effectively was part of the origin idea of the company. So this is part of the founding premise. But of course, now it's time to deliver, right? We've built the infrastructure, we're growing these crops, we're collecting the data. How do we drive that actually back into creating more value with the company? And so I think so that the idea that I wanted to bring to this talk was how in a small organization or with limited resources or however many resources you have, how do you prioritize closing that loop, right? Because there's a lot of work you can do that's really hard and really valuable, right? You can see how much order you're bringing to the world, improving the modeling of your warehouse or logging more things than you were logging before so that you can understand it. But at the end of the day, you've got to think about closing that loop, right? Getting back into, and so what are we driving back into the business so that it starts working better? And so I think of that process as looking something like this, where data is coming from places in the world that you don't control. And of course, we always have complaints about that data, right? It's messy, it's incomplete, it doesn't tell us all the stories that we want it to tell. And so we do a lot of work in this ETL layer, right, where we model data into a well-structured warehouse or some other data store that we control so that it meets the needs of people asking questions. That's great. That's a super important first step. Now you've got structure, now you've got order. The next step is doing something clever with that, right? And doing something clever can mean a lot of things, right? It can mean deep learning, self-driving cars, or it can mean defining a KPI that lets people understand what changed in the business, right? There's a broad scope of clever, but no matter what that clever is, once you've built that part of the pipeline, then you've got to send it back in so that it changes something about your world. And so that's either, sort of the way I'm describing it, through some sort of reporting where you help people understand the world and then they make decisions, or as a data product back into the system, right? Whatever the application is, whatever the thing is that you're trying to automate. So closing this loop or thinking about how we can build data infrastructure that lets us close this loop as quickly and as lightly as possible was really central to my goal and sort of my strategy in working on this problem at Bowery, because I've been there a year. For 9 of those months, I was the only person doing data work. Right? So I need to close this loop and prove value that we can do these things, that we can say, let's automate part of this process, or let's do recipe search, without spending a year building all of these different engineering projects. And so, sometimes I just like to throw cool pictures from the farm in, because that's a lot of the fun of working here. So this is a picture of our recently opened farm in Kearney. You can see each of these, when I talk about sort of growing areas, each of these is an independently controllable crop. And so it has its own light, it has its own actuation and control, right? So any of the things that we want to know about it or want to control for it is controlled on those units. And so you can think about that as our experimental unit, or as our primary unit of data. And they go as far as the eye can see, because we want to be doing as much of this as possible in parallel. And so this is sort of the icon-heavy overview of the architecture that allowed us to do all of this, to close that loop really lightly. And that's what I've been really excited that we've been able to accomplish as a team, is how easy it has been to connect this loop. So the pieces of this puzzle, and I'll break these into a little bit more detail, but the pieces are, you can see, everybody in this room probably recognizes AWS icons. We were already an AWS operation on the software side, so it made sense to really steer into that world. And so we've got all the data that I don't create, right? From the world of sensors, from the in-house applications, and from things like S3, all hitting the message bus. So we use an SNS SQS message bus that all of those applications are already natively broadcasting everything that happens to them in. So everything that happens is, what's an example? When a new crop is created, right? A new crop is seeded. The software service that manages crops posts a message that says new crop ID 123, and it goes across the message bus. Same with a sensor that just measured that the humidity in the room is 52%, goes across the message bus. Everything goes across the message bus. And so what I do then is just take all of that with Kinesis and throw it into a Redshift load schema. So I just have this whole history of all the data that the company has created. And definitely one differentiating aspect of this world of data is that it's all first party. I don't have any web analytics. I don't have any clicks. I don't have any ad retargeting anything, right? It's all just sort of a universe that we've defined. And so that's definitely like a simplifying advantage. But the result is I have a single world of streaming data coming through that Kinesis just puts all into Redshift for me. And so from that load schema, I use dbt that I think a lot of people here are familiar with. dbt is an open source Python library in which you express templated SQL to ask for models that you want, right? So given, and I'll go into more detail, given all of this data that I have coming into the load schema, dbt is how I define what I want to see in my warehouse. Give me the table of crops. And Sinter is their hosted running service, or orchestration service. And so those tools together is all that's involved in going from this universal stream of data coming in to a warehouse I can work on. The next whole piece here is that sort of whatever tools we want to use, right? The design is just query the data warehouse to define your world, do whatever you want to it, and then put it back on the message bus. And so that's all. I'll get into some examples of different things that we've worked on in that project, or in that portion of the world. But the idea here is just, this is one more piece participating in the message bus world. And so that's how we close the loop. And so now I'll jump into some examples. I think I talked through most of that. This is just the labeled version. But so this is an example of how simple it is, basically. So everything, all messages, all data that happens in our world ends up in this load.messages table. And they all have message types and timestamps. right? So basically every message has a message type, a timestamp, and a JSON payload. And if I want to define a table that has all of the temperature readings, I just select those types of messages out of the bus. I extract from its JSON the values that I care about. I give it a timestamp, and now I have a payloads. And now I have a table of temperature readings. And one thing that dbt has built in is incremental additions to tables like this. And so while this load table gets enormous pretty quickly, you're always just incrementally parsing out the JSON from the most recent records since the last time you've run. So that happens, what do I call that? Streaming load. So Kinesis is handling all the time, giving me new data into my load schema. Incremental extract. So every time we run dbt, we just parse out all of the information that we care about from all the messages that are new. And then the last step of that is that on a batch schedule, so we run hourly, all of the data that we've extracted then gets transformed into things that we care about, right? So we don't care about every temperature reading from every sensor, really, sort of abstractly. We care what the temperature was in this part of the room during this hour. And so in that part of the process is where we do our aggregation, our summary, anything that we need to ask the questions that are important to us. One thing that I've found about this pattern that changes the stress and dependency between the data team and the software team is that all messages end up in this load schema, even if I'm not ready for them, right? Even if, so a constant example is we changed the schema of this event, or we invented a new kind of thing. So what happened recently? We brought online automatic control of irrigation. So when the irrigation turns on and off for every zone. It's a new kind of message, right? Irrigation's turning on at this time. I don't have to be ready to ingest that, right? And I don't have to start polling anything or being ready to pull that into the warehouse when that event starts. It's waiting for me in the load schema, right? When that starts happening and going over the message bus, there are now irrigation on and irrigation off messages. And I can write this incremental extraction 3 weeks later when I get to it and get all of that historic data about when the irrigation came on and off, and then sort of catch up and do that modeling work. So it's really helpful for new things. It's also really helpful when something changes. There's never anything lost, right? We have the whole history of all the data that was recorded, and we just have to do whatever SQL might be necessary to get that back in the shape that we want it to be in. And then the last piece of that closing the circle idea, closing the loop idea, is that whatever you're doing with that data that's in the clever AI bucket, whatever tools you're using, the only requirement is you have to be able to post whatever you're creating back to the message bus from that. And so this is an example. This is an abstract example where we made a clever prediction of 42, and that's all it takes in Python to put it back on the bus, right? So we're all in the AWS ecosystem here. So if you're implementing something using a tool like TensorFlow or like Google OR tools, at the end of it, all you have to do is say, and here's the new information that I created. So I'll go into a couple of specifics. One other thing that I think is just so cool about being able to stand this up, especially in a small company, is this is all infrastructure that will continue to work for the next couple of years. We'll definitely run into scaling challenges along the way. But we're running tens of millions of messages a month, right? Which is not big media company big, but it's one person data team pretty big. And all of these tools come together for less than $1,000 a month, right? And are pretty plug togetherable without a ton of I wasn't a data engineer before this role. I am still not a data engineer. But all of these tools really just sort of testament to how much is available in the cloud and the open source tools that we use to manage that, that this is really not something you have to ask your boss to set up, right? It's like, I get these tools, this is doable without a big commitment. Another good picture. So how about some examples? So this picture, again, shows sort of each of these trays of crop needs to get put somewhere in the system. And so an example of one of the problems that we solve is where should we put each tray? Right? If you have someone whose job it is to take each tray from the processing floor and find a home for it, they will be quickly overwhelmed because there are too many choices and too many things to consider. And so this is sort of a classic warehouse problem, right? So where do we put everything that needs to go on the shelves? Except for we have more things that we need to consider. So this is, from a sort of OR perspective, a bipartite graph minimization problem. So what a bipartite graph means is that we have a known set of crops that need homes. We have a known set of homes, and it has to end up one-to-one at the end of the day, right? Every crop needs to end up in exactly one home. Every home needs to contain exactly one crop. And so this graph needs to have a number of edges that is exactly equal to the two sides, and you can't use anything twice. And so Google OR Tools is a terrific, clean interface to this world of solvers that people have, that this field has been working on for ages. And the job is just to express what you're trying to solve, which is non-trivial, right? Expressing what you want out of this problem is not a small project, but the technology layer is terrific to work with. So an example of what we're trying to minimize or trying to express here, we have a lot of the farm is broken up into different areas where you can turn the irrigation on and off. If we're trying to place 50 crops in today, don't put them in 50 different irrigation zones, right? Then we have to turn a lot of different things on and off. You want to pack those crops into the smallest number of irrigation zones as you can so that you have to turn on and off the fewest number of things, right, to reduce the sort of management load. At the same time, you don't want all of those crops to be randomly in the farm, because the whole argument here is that we're giving every crop exactly what it wants. So if you've got an area that is warm and humid for crops that like that, and one that is cold and has tons of bright lights for crops that want that, you have to get those crops ideally all into the environments that they prefer. And then the third piece, or a third example of a dimension we care about, is the retrieval time. So what you don't want to do is put something that you want on next Monday behind a bunch of things that you don't need until next Friday, right? Because then you're going to have to move everything and put it back later. And so we use Google OR tools. We define the problem. We run it nightly. And then that's running on an EC2 instance. When it figures out what its solution is, it posts all of those position recommendations to the bus, and then the front-end application that the farmers are using in the farm listens for those position recommendations and integrates that into the UI that they're using to get that work done. So that's how, sort of following really closely behind what Harlan was describing, that separation of concerns, letting us work on this problem using whatever tools we need to, and then just posting recommendations onto the message bus lets us work on that and iterate without being part of how that gets visualized and communicated to the farm operators. Another cool piece, this is sort of a view from close above a crop, an early stage seedling crop, is we're trying to create new information here, right? We don't want to just take what people have already written down about the farm and then tell them how to manage it. We want to create new information so that people are able to manage in a way that they haven't been able to before. So what you're seeing here is an image looking down at a crop from one of the cameras that we have mounted above every position. On the left is the raw image that's collected. You can see that it's fisheye because we're pretty close to the subject area, so we want to see as much as possible. On the right is a mask that's been applied, indicating what portion of the image shows canopy. All right, so what we're identifying here is what we're seeing in this image that is plant canopy and what is not. Seems kind of easy as a human, right? You just point to all the green stuff. We have green stuff that is not plant, right? You can see some algae growth there on the raft. We have plants that are not green, right? And so this problem is a great deep learning problem. And so this is using in-house training on our image data on top of DeepLab, which is a CNN. And we apply this using TensorFlow on lambdas, actually. So when the cameras take new images, they get passed through this deep learning mask. And what we get is this graph on the left. So you can see over time, the amount of the image that is occupied by Canopy is growing in a pretty, that looks like a real biological process that's happening there, right? You can see the crop growing and then asymptoting at full coverage. And what that lets us do is compare how quickly crops are growing, right? So you can imagine a very simple experiment where you give one crop less light than the other. You can see how much more quickly the second crop grew than the first. It also lets us manage the farm intelligently. Once a crop has closed, right, the canopy has closed, now the leaves are continuing to grow, but some of them aren't getting access to the light anymore. And so that's when you've reached your sort of peak biological productivity, and you want to either take that out and harvest it or transplant it, and so it gets more room. Third, so that was a picture of a crop that's down and being worked on by our farm operators. Third instance of using the third category here is agricultural. This is just such a straightforward machine learning problem or prediction problem. How much will each crop weigh? How much will we be able to harvest from each crop? Right? So a very simple version of this is what's the average that a crop of a certain type has weighed over the last 3 years that we've been doing this? Well, that's great. One of the things that our customers care most about is a reliable supply of this sort of hard to predict commodity, right? We recently launched a partnership supplying sweet green with basil. So if you go to Sweet Green, there's one right across the street here, and get a salad with basil in it. It could well have come from one of our farms. What they care about most is being able to just keep that basil coming in the door and not worrying about it, right? They have a supply chain problem. And so what we can do is say, given all the crops we've grown, given all the crops we have in the system right now, how much light they've gotten, how much water they've gotten, and how much we've been able to measure their canopies growing, or what rate that canopy has been growing, how many pounds are we going to be able to ship on Tuesday? Right? We can have very granular, very specific production forecasts so that we can be an agricultural supplier that works more like a manufacturing supplier, right? And say, we know exactly what we're going to deliver you and when it's going to get there. So this is what closing the loop looks like to us. We take all the data of all the different kinds that we get from our IoT world, from in-house applications, from S3 and other data objects. Everything's coming over the bus. We let Kinesis put it all in Redshift for us. We use dbt to transform it all into a warehouse that means the things that we want it to mean. And then whatever cool AI project that we're working on, we put that information back in the bus so that it can be integrated with the other processes. Data team of one was the story when I started. It's not anymore. So Henry and Kevin on the software side, huge in helping to design this message bus architecture from the beginning. And then Say, Marianne, and Katie on my team now doing data science and computer vision. And one thing that's cool with having a consumer-facing brand is you can come see me after this in office hours or on Twitter. You can also stop by a Whole Foods, pick up some arugula or some kale or some butterhead, and close the loop that way. Thank you.
So if you have a prediction on the product weight and it kind of comes in, the actual is less than the predicted, if you need to deliver what was promised for the client, what do you do?
Yeah. So variability is part of the forecasting problem, right? And so part of the production planning process is not just having a point estimate, but having a confidence interval on what we will deliver. And so developing models to us means being unbiased, but also decreasing that uncertainty. Because what we end up having to do, and I think what a lot of sort of production processes do, is not plan to sell everything that you expect to grow. And so if our forecast says that we will grow 1,000 pounds next week, we'll probably commit to sell some fraction of that, maybe 900 of it, to account for the fact that we expect variability there. So we take a statistical approach to avoiding shorts, but obviously the better we can get at that prediction, the more efficient we can make the farm in terms of productivity and selling everything that we grow.